Hey physicists, well you made it to scenario 4, so nice job. One more to go. This one's kind of interesting, and part of the reason that I chose it was because it looks very similar to the lab that you're working on as well. So there's a picture up here to kind of give you an image of what we're talking about. And it says to calculate the magnitude of the force a person must exert on a string attached to a ball that is making it's making the ball revolve with a velocity of 7.5 meters per second in a horizontal circle of radius 0.6 meters. So this looks a little bit like the Addams family with the thing, which was the hand, but you can imagine also that this is attached to a body, et cetera, but whatever. So anyway, part of the reason I like this problem is because it looks at the forces that are acting, and I just think it's kind of interesting. All right, so it's got a picture that kind of gives us the free body diagram already, but because we like to draw free body diagrams, we're going to go ahead and draw that again. So the forces that are acting on the ball are, of course, the force of the earth, the force of gravity, and then the tension force, right? It's got a string. The thing that I think is kind of cool here is that the string cannot pull directly horizontally. If it did, so don't pause the video and stop here, but I just want to show you. If it did, if that was the tension force, then the ball would accelerate downward. Do you see that? Because there's nothing else counteracting the downward force of gravity. So that means that the tension force actually has to go up at an angle like this. That's kind of a severe angle, but you get the idea. So this is the force of the string on the ball, Ft, so that there's some part of that tension force that's counteracting the force of gravity. So I like this problem because it's nice that you can actually see that it's actually technically impossible to swing that ball, or in our case, the rubber stopper, at exactly a horizontal circle. You can't do it. As much as you try, it's just not physically possible. I'm going to break this up then into an Ft in the x direction and an Ft in the y direction, okay? It's just kind of a neat way to see this. So now if we take a look at this, the forces that are acting in the x direction, or the force that's acting in the x direction, is just the tension force in the x direction, and that's what is causing the circular motion. That's what's causing the centripetal acceleration. So if we look over at our picture here, so this is our big circle, right? It's kind of at an angle. And the thing that's really, really pulling it in is just that tension force in the x direction, okay? So that's causing the centripetal acceleration, m times a sub c. And that's it going in the x direction. In the y direction, we've got F Ty, and we've got, of course, the force of gravity, Fg. That one's going in the negative direction. And again, if you've got your ball um, going around in a circle in what is a horizontal circle, there should be no acceleration in the y direction. Okay, so those pieces are pretty important. Let's go ahead and write down our givens, and then we can figure out what to do with all of this information. So it says that the mass of the ball is 0.150 kilograms. Okay, it says that the velocity is 7.5 meters per second, and it tells us that the radius of the circle is 0.6 meters. Okay, so that's this value right here. Okay, which is going to be a little less than the length of the string, because the length of the string will be just the hypotenuse. All right, and then what we're trying to figure out is Ft. So we're trying to figure out that tension force. And so we're going to have to figure out both pieces of the tension force. We're not going to worry about the angle or anything. It just says the magnitude. But in order to do that, we actually have to solve both of these problems. So let's start with the top one, because it's on the top. So Ftx is equal to m times a sub c, and we know m, and we can figure out a sub c because we know that the centripetal acceleration is v squared over r. So Ftx then is going to, let's just go ahead and plug in some numbers, 0.15 kilograms times 7.5 meters per second. Remember to square that value and then divide by 0.6 meters. Okay, so you go ahead and get out your calculator and plug that in as well. When I did that, I got 14.1 newtons. Okay, so that's the force in the x direction that's keeping the ball moving in a circle. In the y direction, we can figure out Fty because that's going to be equal to the opposite of Fg. So it's just going to be m times g. Okay, so Fty is just the mass, which is 0.150 kilograms times 9.8. Again, just to reiterate, we already took that negative into account. That's right here, okay? So that means we don't need the negative sign in our calculation. And so we find that in the y direction, the tension is not very big, right? Especially compared to the other one. It's only 1.47 newtons, but that's a non-negligible number, okay? So now, in order to find this tension force that's pulling up at an angle like this, well, it's just the hypotenuse of our right triangle. So here's Ftx, and here is Fty, okay? And so then we can just go ahead and find the hypotenuse using Pythagorean theorem, right? So Ft is going to be equal to, well, Ft squared is equal to Ftx squared plus Fty squared, right? A squared plus b squared equals c squared. So then we can use that to say that Ft is equal to the square root of Ftx squared plus Fty squared. Plug in some numbers, so that's going to be 14.1 newtons squared plus 1.47 newtons squared. Go ahead and plug that into your calculator. Take the square root of 14.1 squared plus 1.47 squared. Again, square root it, and I got 14.2 newtons. So you can see from that that it's really close to the tension in the x direction, but it's not quite the same. There you go. Happy physicsing.